The problem states that we have triangle ABC, which is an acute angle triangle with AB less than AC, orthocenter H, circumcircle rho. M is the midpoint of the minor arc BC on the circumcircle. Suppose MH is equals to radius of the circumcircle, which this is given, and we need to prove that angle BAC is equals to 60 degree. So I will take you to the geometry part. This is the triangle ABC and the circumcircle rho. O is the center of the circle, H is the orthocenter. So this AH, which will be perpendicular to BC, and this O, if we draw perpendicular to this chord BC and extend it to the circumference of the circle, this point will bisect this arc BC. By simple geometry that we know that from circle, if we draw perpendicular to a chord, it divides into midpoints intersected at the midpoint, and if we subtended symmetrically, it bisects the arc also. So here you can see that OM will be R. R is the radius of the circumcircle. I have assumed its value R, and OA will also be R. Now if you see, both AH and OM are perpendicular to BC, so they will be parallel. Hence they are parallel, and OM is R, and we are also given that HM is R. So by parallelogram you can see that this will also be R and this will also be R. Simply by parallelogram equations you can see that, which will give us that AO is parallel to HM also, because both are R. So between two parallel lines, if two distances are equal, they will be parallel to each other. Also there is a possibility that H can lie outside the triangle, then that it will be isosceles trapezium, but it is not possible here because in the question we are given that ABC is a acute angle triangle, hence the orthocenter will lie inside the triangle. If you don't know that, you can try it by just drawing the perpendiculars in an acute angle triangle and obtuse angle triangle. You will see that it's simple. So that I have written it. AOMH has two possibilities, rhombus and isosceles trapezoid, because of the H can lie inside and outside. Since it is an acute angle triangle, so rhombus is the case. Now in the triangle ABC, so here I proved that AH is equals to R by parallelogram, rhombus, using the rhombus property that all sides are equal, AH will be equals to R. So now if you see in a triangle ABC, if let's say H is the orthocenter of triangle ABC and draw two perpendiculars AD and BE, I will use sine rule. A by sine A is equals to B by sine B is equals to C by sine C equals to 2R. And then if you see in triangle AHE, angle HAE will be 90 minus C because of the triangle ADC. This is 90 degree. And in triangle AHE, if you see, since angle AEH is 90 degree, angle AHE will be angle C. A bit complicated, but you can see it in the diagram. It's simple. So in triangle AEB, if you see, in triangle AEB, if you write cos A equals to, that will be AE by AB. So from there we have that AB as C. We write that as, it's a normal nomenclature that we write AB as C and BC as a small a and AC as a small b. So using that I am writing AE as C cos A. So from there in triangle AHE I will write sin C. Sin C will be this one I am using the sin C will be AE upon AH, AE upon H, and from using the value of AE from here I am writing as C cos A and sending AH this side and sin C in the denominator, and from sine rule I am writing sin C, I am writing C as 2R sin C in the numerator. By after putting those values you will get AH is equals to 2R cos A. Now since we have written AH as 2R cos A, and here we have get the result that AH is equals to R. Now using both the equation I will equate them, and from there I will get R is equals to 2R cos A. From there I'll get cos A equals to half and A is equals to 60 degree. Hence proved.